the space variable actually. So it's an integral with respect to the space variable. So what I can do, I can rewrite this expression as say 1/2 of d by dt of say 0 to pi and u square dx. Okay, so I can pull this derivative out of it, and the rest of the term is going to be the other term on the other side is going to be this actually. So let's rewrite this equation as a times 0 to pi and ux square dx actually. So we can have this. Now a is a positive number, okay, and ux square is a non-negative integrand. So this integral is non-negative. So this entire term is basically non-positive. In other words, that this is less than or equal to 0. So we can treat this guy, which is precisely same as this, okay, as the energy of the system. So if I treat E of t as this expression as E of t, the energy of the system, then I can show, then I have shown actually that the energy of the system decays over the time, and hence the system is dissipated. Okay, and this is one of the reasons that heat equation in one dimension in real variables goes to an equilibrium state actually, while the wave equation does not. Okay, so we can't show a similar kind of a property for the wave equation. Okay, so I'll put the notes and you can get the details from there actually. So a dissipative system goes to equilibrium state, and a non-dissipative system, so it does not goes to an equilibrium state. Keep in view, both of the equations are really are linear actually in one dimension. So they are linear equations. Okay. Can we say something more about it, that why we have this situation? So one of the things that we identified is that both have a same stationary solution, a unique stationary solution, that's a common in both, and both have a different long-term behavior. And why they have different long-term behavior actually, one of the reasons is that in case of the heat equation, the energy decays over the time, while in case of the wave equation, energy does not decay over the time. The energy is conserved in both cases actually. So this is law of conservation of energy is never violated. Okay, so I'm just doing this stuff by waving my hands, okay, because I know that this is pretty much a standard PDE stuff actually. What is the second thing? Another interesting thing, the difference that that makes heat equation different from wave equation in its behavior in long run is basically the smoothing property. Okay, so the smoothing property of heat equation actually. So what do I mean by that? So the heat equation, or the solution to the heat equation, has this smoothing property. So what do I mean by that? So what does this mean is that no matter how much rough initial data you take, okay, rough, discontinuous, no matter random, no matter how rough initial data you take, initial data you take, okay. In other words, no matter how irregular and crazy the initial data is, okay, the initial state is, take the U will smooth out, take the solution U will be always C infinity, it will be always smooth actually. Okay? So even if you begin with a very irregular behavior, okay, of U, but the solution after some time is going to become smooth actually. So it's always, the solution is always smooth actually. Okay, the solution is always smooth. While in case of the wave equation, you don't have this property. Wave equation does not have smoothing property. And what do I mean by that? That if you take a rough U naught, okay, the rough initial data, then this irregular nature or the bad behavior of the initial data will actually propagate will kind of propagate along the characteristic lines actually. So I hope you also remember this basic terminology, from your PDE course, the first PDE course, characteristics, lines. Okay. So the heat equation has smoothing property. In other words, no matter how rough initial data you take, you will always the U is going to always be solution actually, it is going to be smooth. While if you take the rough initial data in case of the wave equation, the roughness of the initial data is going to propagate along the characteristic lines of the solutions actually. Okay, so this is not, so the impact of the roughness will show its impact on the solution. So the solution, is not necessarily smooth, it may be rough as well. Okay, so it kind of inherits the roughness from the initial data. So that's what another thing that makes heat equation and wave equation different, and this is also one of the key reasons that you have an equilibrium solution for the heat equation while you don't have an equilibrium solution for the wave equation. Okay. So obviously I can't get into the all details of it. So what I would like to say is that read the pages 221 to, okay, for the more details, read 221 to 225, okay, from S. Zhang, Nonlinear Evolution Equation, the book that we are following. Okay. Evolution equations. So read out this stuff and you'll find, the things in a more concrete manner. So a parabolic equation and a hyperbolic equation. So heat equation is parabolic in its nature, and wave equation is hyperbolic in its nature, are behaving differently. Now, if you have this difference in linear equations actually, think of the nonlinear evolution equations. The cases would be even worse actually. Okay. In other words, we can ask basically fundamentally, so if you have a nonlinear wave equation, evolution equation, and you solve it, you have its global existence and some of the, say, regularity properties of the solution, okay, of the initial data, then you can ask, you know, the similar kind of the questions there actually, that what is the energy of the system? How does this energy, you know, propagate actually? You know, does that nonlinear equation or the solution of nonlinear equation has this smoothness property or not? Okay, so these are going to play, these basic two conditions are going to play the fundamental role in determining the behavior of nonlinear evolution equations, but there are more than that actually, obviously. You know, these observations are about the linear evolution equations, while for nonlinear evolution equations there is more. Okay, so how are we going to proceed? How are we going to proceed? We're going to proceed in this manner. So what is the bigger aim of this set of discussion? The bigger aim of this set of discussion is that, okay, if you have a nonlinear evolution equation, you know, what interesting questions you can ask about investigating about the nonlinear behavior, the long-term behavior of the solutions of those equations actually. Okay. There can be many ways to proceed, but as I said that if you're going to read from, you know, the pages 221, 220, 225, you'll find things in a more detail, okay, or in a more concrete manner, the things that I'm saying. So to explain these differences in a more concrete manner, say for example, let us consider a nonlinear parabolic problem actually. Okay, so imagine you have this ut plus u plus f of x u, so the nonlinearity is in x and u for all x and t in from say omega cross 0 to plus infinity, while u say vanishes on boundary and u at t equal to 0 is initial condition where omega is a bounded domain in Rn. So omega is a bounded domain with C infinity boundary gamma, okay, and f is a smooth function. F is a smooth, say, function in its dependent variable. So, you know, so let us consider this equation, or this kind of an equation. So this is not just one equation, obviously, this is a class of the equation, class of the parabolic problems actually. For such kind of equation, and this is just one example, okay, so the theory is kind of more applicable, the abstract theory that we're going to do is more applicable to not only kind of this class of problems, but you can apply it to a more bigger class of the problem basically, but to really talk about things in a concrete manner, let's consider this problem. Okay, so you have this parabolic problem, u vanishes on boundary, initial condition is u naught, and the domain is bounded, and the boundary is smooth, and the function f is smooth as well in its variables. So what kind of problems that we can ask? So suppose we have a global solution of this problem. So we have already dealt, this kind of problems through semigroup method for in variety of situations, through compactness method in variety of situations. So suppose we have a global solution to this problem actually. Okay. So suppose we have global solution to this problem. So this or any other nonlinear evolution equation, doesn't matter. This problem. Okay. Now, as t goes to infinity, there are three possibilities actually. In other words, in long run, the long-term behavior of, say, this evolution equation or such kind of evolution equations, or even a more general class of evolution equation, can show the three kind of the behaviors actually. So the first thing that it can exhibit or possibly do is that it can show that u becomes unbounded in certain norm. U becomes unbounded. Okay, so it's not controllable. In other words, that in long run it just blows up in certain norm. Okay, it's unbounded in certain norm. So this could be one of the behavior, that it blows up in certain norm. So that could be one of the possible behavior. The other possible behavior could be that u is bounded, okay, in other words the solution is bounded, okay, but does not converges to a function in x, in certain norm, okay, in a certain norm. Okay. So in a space variable, so the one situation could be that it blows up as t goes to infinity. The other thing could be like the wave equation actually. The solution is bounded, but it doesn't goes to a specific function in certain norm, okay, or it goes to. The third property could be, or the third possibility could be for this problem or such kind of evolution equation is that u converges to a function. U converges to a function in x, okay, and you call that convergent, which is you call that function to which u converges in long run an equilibrium. Okay, so equilibrium solution. Okay, so equilibrium point, like the heat equation. In heat equation, you have an equilibrium solution in long run, you have an equilibrium point to which U converges in long run, okay, that is 0, while in case of the wave equation, it is bounded in long run, but it does not converge to any specific function basically, rather it shows a periodic behavior in long run. So this is one set of questions that you can ask about. So this evolution equation or such kind of other evolution equations actually. Okay. So when you're going to read the notes, so there's a very interesting literature review of that what people have done in different dimensions with the different assumptions on F about, say, this kind of problem actually. So I'm not getting into the detail, I'm leaving this to read it to you from the book actually. The problem that we're gonna discuss in this chapter, the set of problems that we're going to discuss in this chapter and in this set of discussion are the evolution equations that we're going to discuss in this set of equations, in set of discussions. We can categorize those problems of long-term behavior for the evolution equations that we are interested in into the two categories actually. Okay. So in the first few discussions, okay, we will deal with the first category of the problem, and then we'll talk about the second category of the problems actually. Okay. So what is the first category of the problem? It's just a brief review. The first category of the problem is to basically is the question to investigate the behavior of the solution U as t goes to infinity for an arbitrary but fixed initial datum actually. For arbitrary but fixed U0. Okay. So in other words, that you have a problem and your U0 is arbitrary but fixed, not necessarily this problem, could be other problems as well, and try to investigate its long-term behavior, or in other words, try to investigate that in long run which of the situation would hold actually. That either is going to explode, either is going to blow up in long run, either is going to stay bounded but does not converge to anything, or is going to converge to an equilibrium point actually. Okay, but we are going to ask such kind of questions for a variety of evolution equations where the U0 is a fixed arbitrary constant. The second category of a problem, which kind of really generalizes this approach, is to ask about that rather than investigating the problem for a fixed but arbitrary initial condition, let's try to investigate the long-term behavior of the solution, okay, for a bounded set of initial conditions, in which initial conditions. So this would be really the last part of this series of lectures actually. It's a bounded set of initial conditions. So you're going to have a set and say, I don't know, pi, okay, which is bounded, and you will try to investigate that if you choose the initial data from this bounded set, how does the U behaves in long run? In other words, which of these three situations becomes true for the solution of the equation actually. Okay? And another thing that we're going to deal in this situation is basically in this second category of a problem is that we will try to study the global attractors for the solutions of that. In other words, that is the set of orbits are the orbits of the solutions corresponding to the initial conditions in this bounded set are in long run sucked up by attractor actually. Okay, do they stay in a kind of a compact set? So we'll get into the details. So we'll do an abstract result and we'll apply that abstract result to investigate some of the evolution equations. So summary is this. So in this set of discussions, we are now moving towards studying the long-term behavior of the problems, and we will consider the problems in two categories. By problems I mean evolution equations, nonlinear evolution equations. We'll consider the two categories of the problem. First, we will try to consider the long-term behavior of the evolution equation for fixed initial datum actually, but arbitrary initial datum, and then we will like to study some of the abstract results and then apply it to the concrete cases to the situation where the initial data, varying initial data may be chosen from a bounded set actually. Okay. So this is what is really the bigger picture. Okay, you can get this bigger picture in a more concrete manner from the pages that I am referring now. Let's start our concrete discussion. So let me give you a bit of a lemma, a very interesting lemma that is going to allow us to solve a category of the problems, a category of the evolution equations too. So that is going to kind of help us to study the long-term behavior of a class of the evolution equations, a particular class of the evolution equation. Okay. So what I will try to do, I'll try to do the sum part of the proof of that lemma, that interesting lemma, and I'll leave the rest for you to figure it out, or maybe I'll refer to a paper to you that you try to figure out the complete proof of that lemma that I'm just going to write, and then I'll apply that lemma to a concrete problem, a reaction diffusion equation, and I'll show that how that lemma allow us to study the long-term behavior of that reaction diffusion equation actually. Okay. So let's move ahead. So let me give you the lemma. Okay. So the lemma needs a bit patience. Okay. So imagine I have a time. Okay. With the condition that this time is positive. It could be finite, it could be infinite. Okay. And suppose that I have two functions, say y of t and h of t. So these functions are non-negative and continuous, non-negative and continuous, on the interval 0 to t, and these two functions satisfy following set of constraints, following conditions. Satisfy following. So the first thing is that y satisfies a quadratic differential inequality that goes